So we're going to start with some of these practice exam questions because next week you have your first exam. The material on Monday is where we'll wrap it up. And so everything up to Monday can be on the exam. Remember, it's 30 of these. But before you give me that, oh my God, face. How many points is the exam worth? 4 points. Sure, it is now. No, it's worth it. So my exam uses practice to get ready for the ACS final exam. Because you all remember, huh? Oh yeah, it's like real low. So it's worth 30 points. It's worth the same as an assignment. So I have it set up that you could technically bomb all of them and still get an A. I want them to be practice. Okay. I want you to practice getting those 30 questions done in 50 minutes. So that on the final, when you have 70 that you have to do in like an hour and a half to 2 hours, you'll be okay. Because if you remember taking that last semester, that is not a nice exam. And some of you are going, I scored like a 40% law. I did so horrible. Like, actually, you're in the top 10% of chemistry students in the country. So let's be realistic about how this exam is written. So who can answer these? I think just once. I want to do like one of the biology questions. I want to put which one of these is the most correct?
No. Every single exam.
How'd you do with those questions?
You kind of just learn over time. When the first exam, I was like, okay.
I also don't ask true false anymore. My first year students told me no matter how you write them, they think it's a trick question. What do you think the answer is to number one?
Also, this is off topic, but every single class I've been to today has been like ridiculous this month. Just 5 episodes.
Apparently, people like early weekends.
I do. I do nothing.
I tell you what, like, there's going to be a Friday if we come in and it's just like 5 of us. We're going to give out like ridiculous bonus points.
Today, please. This is sarcastic.
I mean, like the kind of bonus points that when other people hear about it, they're going to go, oh.
Yeah, that's why we should start together all the ones that we will do it. Exactly. Please.
How many people are missing today?
Number 5. Yeah, we have out there with those stuff.
If it happens again, we will. Right now, your grades should be fine where they are, but yes. Okay, so you said B, you said C. I'm going to C. You said C. What do you need? 3 more from the peanut gallery. The answer is not D, it's E. Let's talk about why. So we're doping a silicon. Remember, the materials originally all silicon, so doping is we're putting in atoms, and removing some silicon atoms, putting in new atoms. Now, phosphorus and arsenic have more valence electrons than silicon, so that doping those in will make it an impound. Okay. Protons or the mobile charge carriers, never. Never. It's always electrons. So electrons are going to be involved in current, so it's always electron. It does not conduct electricity as well as pure silicon. That's kind of the trick part of this one, because even though this is going to be a p-type where you're going to have electron holes, just the fact that there are holes there ready to receive electrons from another material, this conducts so much better than silicon. So that C is kind of like can be tricky with this one. So they're all true. Oh wait, none is true. Sorry. Maybe I don't want to be here on a Friday. So let's do the second one. 2 of those you can automatically get rid of. Why? more current. So anything that says decreased, gone. Learn techniques like this. This will help you on exams.
Is it? I don't know.
It is a.
Okay. I was looking at P-type, but I don't know
Mhm.
if it's going on with the P-type and P-type.
So boron is going to have less valence electrons than selenium. Again, when you take an exam, you're going to have a periodic table. If I don't care where it is up and down, if an atom is to the right, it has more valence. If it's to the left, it has less valence. So find where selenium is, you'll find boron to the left, less valence, P-type. All right, some things we got to go over into the chapter. Molecular solids, we've been talking about our cubic structures. You can kind of see it now. You can see that in the molecular solids, you're going to have molecules at each one of the cubic lattice sites. So entire molecules. On the far right, you see the ice crystal. So you can start to see why solid ice is less dense than liquid water. I almost said liquid ice. If I ever say liquid ice, you can throw something at me. No,
No?
I just mock you a little bit. But you see how they all line up and you get these directional hydrogen bonds. So of course, that's going to cause all these molecules to space out, making it less dense. Ionic solids. So again, you can have simple ionics where you just have like your sodium and chloride in different positions, or more complex where you have polyatomic ions. Now, this next part is going to take some more visualization that you've not done before. So it's going to be a little difficult at first. Because we start talking about the types of holes that these individual stackings, like the closest packing, will produce. Because usually you have one of the ions at the lattice positions. The other ion will fit inside the holes based off the stacking of the other ion. So you have trigonal holes, tetrahedral holes, and octahedral holes. We're really going to be primarily concerned with tetrahedral and octahedral. So I went ahead and put like a specific tetrahedral hole up on the top left because they're kind of hard to see when you first start. Because take a look here. Look at this one on the bottom right. That one is your that's your tetrahedral hole, and you have to be able to look and say, well, where's my tetrahedral? There's your tetrahedral. And you can see the hole sitting right in the middle of it. Your octahedral holes, these are going to take two configurations, face-centered cubic and body-centered cubic. Most of the time we'll be working with face-centered. So do you see how all of your little atoms or ions are in the face-centered positions? So when you're looking at how many holes are in here, you have one entire hole right in the center. Okay? Because again, that's a face, 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 and then you have the corners. And it's kind of hard to visualize your first time through. Now, the rest of the holes on this face-centered cubic are on the edges. So you have to figure out how much of a hole a single unit cell gets when it's on the edge. So a hole that's on the edge is shared between how many different unit cells? 4. 4 unit cells. So each unit cell is going to get 1/4 of an edge, either atom, ion, or hole. Okay. So now we have corner. Remember, your corners are 1/8. Faces are 1/2. Edges are 1/4. And when you have a tetrahedral hole, anything in a tetrahedral hole is either the entire hole or the entire ion. Okay? So you just count how many you have. All right, so here you have your face-centered cubic in the middle. Your octahedral holes can also shift to a body-centered cubic. So here's your body-centered cubic. This time your holes are going to be on the faces and the edges. Okay? So you have 12 edges, 6 faces, the 12 edges. So let's think about that. So if I have 12 edge holes, and I get 1/4 of that hole per edge, that gives me 3 total. Okay? The faces, if I have 6 faces, and I get one half of a hole per face, that gives me 3. So your body-centered cubic gets 6 total holes. Okay? Versus your face-centered cubic. So again, you have the 1 in the center, and then you have 12 edges times 1/4 hole per edge gives me 3. So 1 plus 3 is 4 total holes. You will get used to it. Or you won't, because we're done with this. We're done with this after this chapter. We're going to go on to other stuff. But for those of you who really like crystals. Okay, now what you want to be able to do is figure out what the chemical formula for a ionic compound is based off the structure. So look at the calcium fluoride here. Yeah, I gave you the formula, but does this ratio hold up? See how the calcium and fluoride is in a 1-to-2 ratio? So let's count that up. You see the calcium, do you notice that those are at the face-centered cubic positions? Okay, so if all my calciums that are face, so let's do calcium to fluoride. If all of my calciums are a face-centered cubic position, how many do I have? How many atoms did you get in a face-centered cubic unit cell? 4. No, 4. Well, so look, you have, okay, so you have your all your corners. That's 8 corners times 1/8. That's 1. Then you have your 6 faces. 6 times 1/2. That's 3. Oh yeah. So that's going to be 1. So you get 4 of your chlorides because they're at the face-centered cubic positions. Now, your calcium, your fluorides. What does that hole look like? What did we just talk about? What does that look like? See how they're just kind of floating there in the middle? What kind of hole does that look like? That's a tetrahedral hole. So how many of those fluorides do I have? Remember, tetrahedral holes give you entire ions. So 8, just count them. When you have things in a tetrahedral position, just count them as a whole. So this gives me 4 to 8 or 1 to 2. So it holds. Well, so like we talked about, your body-centered cubic has 6. Your face-centered cubic has 4 holes. Your tetrahedral holes. So you see how the tetrahedral has basically a face-centered cubic setup with the holes in the center. So your face-centered cubic has a maximum of 8 holes. 8 octahedral holes. You just have to notice if the ions are in the octahedral position. Tetrahedral. The face-centered cubic has a maximum of 8 tetrahedral holes. I want to be done with this chapter. Okay, now, you see on the bottom left, that's a hole or an ion or an atom being shared when it's on an edge. You see how it's shared between the 4 unit cells? Okay, let's look at sodium chloride. Do you notice how sodium, okay, just look at the chlorides. What is the positioning? What's the unit cell for the chlorides? Face-centered cubic. Face, 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 face. And so then your sodiums are going to be in the hole positions. So does this hold? All right, well, my sodium chloride has to be 1-to-1. Okay, so if my chlorides are at the face-centered cubic position, that gives me how many? 4. My chlorides, I have 1 in the middle. Oh, yes, it should. Now, the chlorides are in the face-centered cubic octahedral holes. Okay, the sodiums, it's one of those. Okay, the sodiums, we have 1 sodium in the center. Okay, and then the rest of them are on edges, 12 edges. So how many does that give me? 4. Because I have the 1 in the center, 12 edges times 1/4 per edge. So that'll give me 3 for the edges. So that gives me 1 plus 3 is 4. So that gives me a 1-to-1 ratio. So this holds. It's a 1-to-1 ratio. So it becomes 4-to-4 or 1-to-1. This one, zinc sulfide. Your zincs, what kind of holes are those in? Tetrahedral. Now you notice it's a few less than the last one. So when it's in a tetrahedral position, you're just going to want to count them. Now, your zinc is a +2. Your sulfide is a -2. So they have to be zinc 2 plus, sulfide 2 minus, 1-to-1. So how many zincs do I have? They're in tetrahedral holes, so you just got to count them. 4. Now, the sulfides, what kind of crystal positions are those in? Face-centered, which gives me how many sulfides? 4. Or 1-to-1. So it holds. So you want to be able to do this backwards and figure out what the chemical formula is from these structures. Okay, like go through how many edges do you have, how many corners do you have. So you're going to want to be able to do that. Mm-hmm. Crystals are very, very exact. Which I always wondered why people wanted real diamonds and not laboratory ones. You know what the difference is? Real diamonds have flaws. Laboratory diamonds are almost perfect. Seems odd. Why do you want the one with flaws? I don't get it. I don't get it. Okay. Look what's happened here, though. So we have cesium chloride, same chemical formula, like same chemical structure as sodium chloride, 1-to-1. But now you notice it's switched to a body-centered cubic configuration, where all of the ions are at lattice points. The chlorides take the simple cubic lattice sites, the cesium takes the body-centered. Now there's a reason for this. This, you can actually look up ionic radii based off different periodic, so there's periodic tables that'll tell you. You want to take a ratio of the ionic radii. You notice here how the ratio of the radius of cesium to the radius of chloride is 0.92. That means your cesium has, volume-wise, has become about 92% of your chloride. Once you cross a ratio of about 0.732, your crystal cell, your crystals will shift from the face-centered cubic to the body-centered cubic. Okay? So you're going to want to make sure you're paying attention to that. Who can answer this one? In particular, look at it's MX2, you have to have a 1-to-2 ratio. Which one of those setups gives a 1-to-2 ratio? Nope. So let's look at that. So if I have my M at the corners, of course, that'll give me one of those. But the X ions, so if I have all of those at the faces, for the faces, it'll give me 3 of them, 2 more tetrahedral holes. So that'll give me MX5. I know people don't like to be wrong, but you learn when that happens. Most people are like, I won't say a word until I'm right. Well, see ions at the corners, that'll give me one of those. It is A. Mhm. 8 at the tetra, so see corners in each face. So the corner will give me 1, each face will give me 3 more. That's 4. And then the 8 reduces to 1-to-2. So if these were, so this one, M, so the M at the corners and at the faces, that gives me 4. And then, see that last one doesn't even make a whole lot of sense. Sometimes you have to read them. If they don't make sense, they probably don't. Because usually your octahedral centers, unless they mean tetrahedral, and this was a typo, but this is from the question bank that I have. Yeah, because usually your octahedral centers would be like edges. So but you're not going to have 4 of those per edge. So this was probably a typo from the question bank, but it's good practice because that selection there, you could cancel it out by going, that just doesn't even make sense. So yes, I would say so. Hang on. Yes, FCC. All right, we'll finish up some of the material from this chapter. Vapor pressure. So you have a fluid, you have a liquid in a container, you cap it. It sits there for a while. Eventually you get a pressure in there because above every single liquid, some of the liquid has escaped into the gas phase. So the vapor pressure is just how much of that has escaped and the pressure that's above that particular liquid. Now, the term that's interesting is volatile. What do you think volatile means? Nope, that's lustrous. So that's what a lot of people think. I guess in a way it can mean that, but for chemistry, what it means is so it's a liquid compound with a very high vapor pressure at standard conditions. So that means like at room temperature, most of it's gas. And so we have a standard vapor pressure, and that's where the vapor and the liquid phases are in equilibrium with each other. Equilibrium will make more sense as we get into future chapters. Now, as a warm-up to the math-centric part of this semester, we can actually start to figure out the enthalpy of a specific phase change. So here we have a nice little equation that relates vapor pressure to enthalpy, but it has that annoying little C in there, which is a constant that's characteristic of a given fluid. Now, one way you can do this is, do you see your experimental graph on the right there? How you've now you have the natural log of the vapor pressure over versus one over temperature, and you get nice straight lines. How does that help me calculate enthalpy of vaporization? What does this formula look like? You've seen it before. Nope. Not really. If I was to pull the slope out of this, what would it be? Mm-hmm. And of course, this R is your ideal gas constant. Remember we talked about using ideal gas constant with enthalpies where there's energies. So your R is going to be your, let's see where I wrote it down. Yep. 8.3145 joules per Kelvin times mole. So that when you're working with energies, this is the R that you want. Now, we can actually avoid that factor of C by coming across if anyone can actually pronounce the second name, I've never been able to. I can do the German name, Clausius, but yeah, we'll just go with that. So how do we get here? You're going to have to make use of something. So if I have, first off, what is Ln? What kind of log? Natural log. So if I have this, how can I combine this? How do I reduce this? Who remembers the rules of logarithms? Any guesses? How do I condense this? I get the Ln of what? Close. You already kind of have that. And that's an identity. You can use that. So the first thing I want to do is I want to take this first equation and solve for C. So that means I'm just going to bring the delta H term to the other side. Okay. Now, remember what we did with gas laws? If you have something that equals a constant, every single variation of this also equals the same constant. So I could have a T1 situation and a T2 situation. And that they're going to equal each other because they both equal C. So be thinking about that since they both equal C and what C actually is. So that means I can have, eventually I'm going to break this down and just call it P1 and P2, but I want to use the subscript so you know it's vapor pressure at T1. Then I can do the natural log of vapor pressure at T2. Remember doing stuff like this with the ideal gas law? Throwing your pencil is not going to help. Now, notice how delta H over R does not have, it's not a delta H1 or a delta H2. R is self-explanatory. That's a gas constant. Why didn't the delta H change based off the T1, T2 situation? So C is a constant specific to what? C is a constant characteristic to what? So you would have to look it up. That's why. Well, so C is a constant that's characteristic to a specific liquid, specific substance. With any substance. So you just look up the C. Now you notice I didn't do delta H1 and delta H2. Why? If both of these equal C, what didn't change? The constant, and what does that mean did not change? Yeah, why is it the same? What did not change? The same liquid. So a liquid has a characteristic enthalpy of vaporization, enthalpy of fusion. And you can look those up in tables. So it doesn't matter what the temperature is, it's the same substance. Now, what I want to do is get the natural logs together on the same side of the equation. So I'm just going to call P8 T1 P1, and then minus ln P2. That is going to give me, who remembers how to factor? Can you do that? A little simpler than that. I'll ask you in a second. Yep. Now, look at the left side. How do I condense that? Mm-hmm. Now, factor out the delta H over R on the right side. What do I get? What's inside the parentheses? Subtracting. And we end up at the Clausius equation. So you see, we can use this to bypass that pesky little constant that we'd have to look up for each individual substance. And I cannot express how much I enjoyed alpaca mellow. You know, it took me moving out here to see a show cow for the first time. I didn't know they could be fluffy. Saw a picture of like here's my show cow. Like, it's fluffy. I didn't know you could do that. All right.
Like some people have certain stations and you can go there to get up and then you brush it and you brush it out so it like sticks out.
Well, my goal now is to pet a fluffy cow. So.
And then it's like you trim the brush and then you trim the brush. So trim the cow.
I've seen people do that with their dogs. Use those little fluffy white dogs and they make shapes and. Yeah, I just want to pet a fluffy cow. I just really want to pet a fluffy cow. I didn't know you could do that, so I found that out. Let's see if we can solve this problem. Now, here's the thing about this equation. It does not matter which one you call P1 or P2 or T1 or T2, just as long as you stay consistent. You match the temperature to the pressure. So I'll show you what I did. So I said T2. What do you think I'm going to do to these temperatures? Now everything's in Kelvin. But why do I need to do that? Because your gas constant's in Kelvin. So make things match your constants. So I'm going to start. Oh, and I remember I cut off a slide, so I have very little room to do this. He's going to start with our equation here. Who wants to start plugging in numbers right now? Like if you were doing this problem, would you start plugging in numbers now? You shaking your head no makes me very happy. I've had people go, just plug them in from the beginning. Those are sad days. Because me, I want to solve, I want to try and at least solve for P2. All right, so then all right, then let's get rid of the negative sign. Now from here, I started plugging in numbers here because how you have to reverse natural logs. Does anyone know how to reverse a natural log? So if I have natural log of x, how do I get x? Yep, so if I exponentiate the natural log, it eliminates the natural log because the natural log is log base e. So kind of like we were doing with pH and whatnot, you take your pH and your 10 to the negative pH. That's because you get the pH by taking the logarithm of the concentration of hydronium. And so regular log is log base 10. So you just whatever log you have, you raise it to you make it the exponent on whatever its base is. That's probably making it more confusing. We'll practice with it. Okay, so my P1. Now I want to know if anyone can tell me why I knew that P1 was 1 atmosphere. Close. Did anyone catch it on one of the graphs? So if you look, okay, normal boiling point, you see that? I'm going to go back up a few slides. Here, you see this line across here? That's your normal boiling point. You see how it's at 760 torr? Normal boiling points are at 1 atmosphere. That's your vapor pressure at the normal boiling point. Oh, I went too far. Okay. So, and this makes this easier because someone type in the natural log of 1. Tell me what you get. Now, this we have in kilojoules per mole, but our gas constant is in joules. So I'm going to make this delta H 59.1 10 to the third joules per mole. Yep. So this whole thing becomes 0. So our R is 8.3145 joules per kelvins times moles. And then we have 1/298 Kelvin minus 1/630 Kelvin. And what we get is negative 12.57. So that's what the natural log of P2 is, all right? Now, I want to know P2. Which means I'm going to do E and then make my exponent my 12.57. This is going to give me 3.47. So start reviewing your natural logs and your exponents, but keep in mind you are going to end up using them a lot this semester, so you should get pretty used to it. I was going to leave myself 2 slides for this, and then I didn't do it. But again, keep in mind, I changed things to match the units of my gas constant. So I changed the delta H from kilojoules to joules, and I changed my temperatures to Kelvin. Yep. This is a gentle introduction to the math intensive portion of the semester. Yeah, okay, let's finish this chapter up. Changes of state. So we've already kind of looked at this. Remember, this is our standard heating curve, where you have your phase change region where it's flat, you get an inflection, and you're going to calculate the heat put in at those points by number of moles times the enthalpy of whatever that phase change is. The sections where temperature is increasing, your heat is calculated by the calorimetry equation, Q equals MC delta T. So here you see a couple of ideas: normal melting point, the temperature where solid and liquid states have the same vapor pressure under conditions where the total pressure is 1 atmosphere. Normal boiling point, temperature where the vapor pressure of the liquid is exactly 1 atmosphere. I want you to know how to be able to read phase diagrams. You see how you have the solid, liquid, and gas on the same diagram, and they're separated. So all of these lines tell you something. Your solid liquid line, that's that line going up between the ice and the water. No vapor exists there. Your solid vapor line, that's that first little curve on the very far left. No liquid exists there. Your liquid vapor line, which is the last part, no solid exists. You have a triple point where all 3 phases exist at the same time. It gives you a pressure and a temperature telling you where that happened. You have a critical point. That's where critical temperature and critical pressure exist together. So critical pressure, if you're at the critical temperature, that's the pressure you need to turn the gas back into a fluid. This actually happens in our solar system. Well, kind of. Anyway, I'm just not sure if that's the critical point where it happens, but on Jupiter, the pressure of the atmosphere condenses hydrogen gas back into liquid metal. The critical temperature, above that temperature, no matter how much pressure you apply, no liquid's going to form. So if anything, Jupiter's not above the critical temperature because it still compresses the hydrogen back into a liquid. And then we have the difference, again, kind of talking about the difference between ideal gases and real gas. So again, you have your van der Waals correction. One of the things about a gas being ideal is it assumes that there's no interaction between the molecules in the gas. Where now we study intermolecular forces, we know that that's not true. You look at the graph on the lower left, you can see that the higher that temperature gets, the more ideal a gas behaves. When you actually get to the critical temperature, you get an inflection point where you're starting to see some of real behavior below the critical temperature, which is going to be pretty much your standard conditions. You're getting a non-ideal behavior. So like that red line there, that's temperature is much greater than critical temperature, you're getting ideal behavior. And that just decreases as the temperature goes down. Okay, welcome to the end of this chapter.